now we are into the second lesson for this unit called The Strength of Acids and Bases and the pH concept. So last year we talked a little bit about pH, but more in a relative sense, like what is the pH of this compared to this. So this year we're going to focus more on what's the pH and how does that relate to whether we have an acidic or basic solution. So we'll talk about reversible reactions like weak acids and bases. So yes, it's about concentration, but it's also about ionization or the percentage of the acid or the base that actually dissociates. And then we'll look at the last lesson for this section, which is titrations. So that is the procedure where you add an acid to a base and looking at when you can get a perfectly neutral solution. Is it really a pH of 7 at equivalence point and that kind of thing. So that's what we're moving towards. Okay, so this is a beefy lesson. You should already be able to distinguish it between an acid and a base based on proton transfer. And today we're going to look at a quantitative way in case you forget which were these strong acids and bases. Bases are a little bit easier to pick out, the strong ones. You should already be able to write conjugate acid-base pairs, calculate pH, H+, POH, and OH. Those formulas were in the first note, and using the different relationships to convert between values. So if you have a base and you calculate POH, changing that into pH, etc. Today we're going to calculate percent ionization, and we're going to use ice to find pH or equilibrium constant values. So sort of similar to the last unit or both last sections of equilibrium where you were either solving for the equilibrium constant or you were solving for X. Okay. So the stronger the acid, the weaker the conjugate base, or vice versa. The stronger the base, the weaker its conjugate acid. And the reason for that is related to the ionization. So the more an acid ionizes, then it's stronger, which means that the reaction has a decreasing amount of reversibility. So then the conjugate base actually is not a legitimate proton acceptor, or in the case of a base, the stronger the base, then the conjugate acid is not a legitimate conjugate, proton donor. So what actually happens when you have, say, for example, you're adding an acid to a base, sometimes people will say, oh, if it's a strong acid to a weak base, then that means that the strong acid makes the pH more towards the acidic side, where it has to do with the conjugate pair of the weak base. The weak base makes a conjugate acid that actually can lower the pH of a solution. It will be a proton donor. So these are important concepts. And the acid strength is proportional to the number of hydrogen ions. So this is the short form for proportional. And the base strength is proportional to the number of hydroxide ions produced per mole. Okay, so strong acids dissociate 100%. So hydrochloric acid is a very common example of a strong acid. I think I said this in the other video. I've never actually seen solid hydrogen chloride. So it 100% dissociates into hydrogen ions and chloride ions. So you can see here, this is not an equilibrium arrow. This reaction goes 100% to the right, which means then that there is no reversibility. So which means then that this is not a legitimate proton acceptor. Okay, so there's 100% ions in the solution. That sucks, sorry. No HCl left. And let me see. Oops. I'll write this in a different spot. No reversibility. There you go. Now it's not over top. Okay, so not a legitimate proton acceptor. Whereas when you have a weak acid, then that means that only about 1% of it dissociates. So this is acetic acid or vinegar. And as you know, you can put vinegar on your French fries and you're not afraid of it burning your esophagus like a strong acid would. And here you can see there is an equilibrium arrow indicating that the reaction can go in both directions. So the acid only dissociates about 1%, which means that there is a considerable amount of the acetic acid left in the solution, and the pH or the strength of the acid on the other side just said that it's depends on how many moles of hydrogen ions or protons are produced. So it has nothing, this itself here, this substance here is not acidic in itself. It needs to produce hydrogen ions. So if it produces less hydrogen ions by dissociation, then that makes it a weak acid. So then because there is reversibility here, that makes this substance here, which is acetate, this is going to be a legitimate base or proton acceptor. Okay, so there's still quite a few acetic acid molecules and some ions, making it a weak acid. The reason it's written like this, you're going to see this often with weak acids. This we're going to talk about in the organic chemistry unit. This is a carboxyl group, those of you that took biology. This makes an acid, a carboxylic acid. Usually these carboxylic acids are weak. So what it's trying to emphasize is that this is actually, let me see if I can get color here. This is actually the proton that's lost. Not these ones over here, because this is connected to the oxygen, which is more reactive than these boring ones connected to the carbon here. But that, it doesn't really matter, but that's why it's written like that, okay? I know that's a little bit strange, but. All right, so on to, oh no. There we go. On to the acid ionization constant, or the equilibrium constant. A for acid, B is going to be for base. And this is going to quantitatively tell us the relative strength of an acid. So the smaller the value of Ka, the weaker the acid. And if you actually look in the back of your textbook on page 803, then for strong acids, it actually says very large. It doesn't even give a value for the Ka. So those ones that are listed there are considered to be large acids, or strong acids. And then the ones that are smaller, we're going to call those weak acids. And we're actually going to use the 100 rule. And again, I said this in the videos for the last section. There are some acids or some situations where I don't think you should use the 100 rule, and your textbook still does. So in this section, so whenever if you are given a Ka value, like an actual number, or asked to calculate it, that means weak. Okay, and why does it matter? Because if it's weak, then you have to do ice. So the problems you would have done for the first lesson of this section you did not have to do ice. Those are considered to be strong acids or bases. Okay, so this says Ha, but really this is just trying to emphasize that every acid has a proton, or it is a proton donor. So the acid dissociates into hydrogen ions and some kind of anion here, which is going to be its conjugate base. Okay, so then we're going to do the same thing, products over reactants. The good news is this year for you guys, all of the exponents will be 1 because we're only going to deal with acids that have, when we do the math, that have 1 hydrogen. So yes, last lesson we wrote the dissociation equations for phosphoric acid, which have 3 hydrogens, and the math gets significantly more complicated. So that would be if you choose to continue into chemistry next year. Okay, so again, you can look up the Ka values. Unfortunately, in the questions in the textbook for homework, they usually they will expect you to do that if you're not given it, whereas on a test or the assignment, I will give them to you in the question. Okay, so then the same thing for a base. So Kb instead of A, B for base. So the smaller the value of the Kb, the weaker the base. The only difference is in the textbook, it's not listed. For strong bases, only for weak. Okay, so these ones here. And the reason for that is when you have a strong base, they will have OH in the formula. Like KOH, NaOH. Okay, and that's how you know that it's going to be a strong base. So the bases listed in the textbook are mostly derivatives. A lot of them will be amines. They'll have some kind of NH, like ammonia, or methylamine, for example, which is the one we're going to use in our example. So now we have a base, which is a proton acceptor, and usually it steals the proton from water, which we'll talk about when we do the problems. And so again, products over reactants, we're only going to deal with one bases that accept 1 proton for now. Okay, so and then this is another way we can convert between Ka and Kb using Kw, which is 1 times 10 to the negative 14. That value is a reference value which was in the first note. So you'll see in these questions, you could actually be given very little information and asked to do many things. Okay. So since strong acids and strong bases completely dissociate into ions in solution, the forward reaction is complete. Equilibrium is not established. You are not going to do ice. Whereas weak acids and bases do not completely dissociate. So that means that an equilibrium reaction is established and you are going to be expected to do ice. So if we have a weak acid, another thing you can calculate is percent ionization. So basically you're looking for what percentage of the acid dissociated into hydrogen. You could put the anion in the top as well. And because of stoichiometry, like I said, they're all going to be 1 to 1. It'll be the same for these two here, like this is 1 to 1. Okay, but since we're dealing with acids most of the time, we like to deal with, we talk about the protons. Okay, similar for bases, except it would be like I said, hydroxide in the top of the fraction, and then the base concentration would be in the bottom. Okay, so let's do some examples. So the percent ionization example, I'm going to actually, there is quite a bit there of hints I'm going to give you in this example. So that's why there are 2 slides for this, or quite a big spot. The calculating percent ionization itself is actually not that big of a deal. So the more you write down, they're gonna these hints will help you for all of these kinds of problems. Okay. So first of all, you have to write your own equation for weak acids and bases showing the conjugate pairs. So an acid is a donor. How do you know that a student has prepared a 0.1 molar acetic acid solution and found the pH was 2.96. Calculate percent ionization. So how do you know it's a weak acid? pH is acidic. It's below 7, but it's not too acidic. It's not like 0.1. You could look up the Ka value. That would tell you. And to be honest, it's a very common weak acid. So if you do enough of the problems, you'll just get used to it. So then when you write your own equilibrium equation, you can choose to do 2 things. So chemists are lazy. Because water is a liquid, we're gonna cross it out in the ice table. So some people will put it in there and some people won't. It really matters more, I think, when you do bases, because when you have a weak base, where does that hydroxide come from? Well, it comes from the water, right? Water behaves like HOH. So it's up to you. So it's going to be a donor, which means you're going to get, let me just see if I can fix that. Sorry, that's not what I want. No. Here we go. Let me just move this so it doesn't look weird. Okay, there we go. Okay, so you're going to get acetate. Again, the proton that's going to be lost in water is the one on the end. Lost on acetic acid is the one on the end. And then when water accepts the proton, you're going to get hydronium, the hydronium ion. So if you choose to not write the water, then you would just write H+. So as the acid has lost a proton, water is going to gain it. The thing that is important, H3O and plus and H+ are used interchangeably. So you can use, like when you do pH, it's like pH3O+ or negative log H3O+ concentration. They are used interchangeably. It just depends if you are a lazy chemist or not. Okay, so the pH is very useful, very, very useful. It can be used to find the H3O+, again, H+, they're used in the same way. Concentration, which is helpful for the ICE table. Okay, so percent ionization is the hydrogen ion concentration over the acid. So again, we are given the acid concentration. We're going to use the pH value to calculate the H+. So 10 to the negative pH. So this is 10 to the power of So you can either use, there should be a button on your calculator. The inverse of log is 10 to the x, or you can type in 10 to the power of, however you do that, on your calculator to the negative pH. So 10 to the negative 2.96 is 0.011 molar. So 0.11 molar divided by 0.1, which we're given in the question, we're given this, is 1.1%. Does that make sense? Yes, because it's a weak acid, so we do not want it to be very high. Okay, so this makes sense. It's a weak acid, and so produces a small amount of ions, and so the percent ionization is low. Okay, so on to tougher questions. So I'm going to do this actually the other way so I can use different colors. Okay, so 0.1 molar solution of formic acid. So again, here's that weird organic acid, carboxylic acid looking thing. Has a pH of 2.38. Find the Ka and the pKa. So if you're asked to calculate Ka, that means it's weak. Because, of course, when you have a strong acid, its Ka value is very large. Not calculated. You are not able to calculate it. Okay, so we have to, that means we're going to do ice. Okay, and we need to write our own dissociation equation or our own equilibrium equation. Whether you choose to do include the water or not, if you're a lazy chemist. Okay, it's an acid. How do I know that? First of all, it says Ka, A for acid. It also says acid in the question. And like I said, there's really not that many options. So if you do even a few of these questions, they're all the same basically. Also, this is acidic. This pH, it's below 7. Okay, so there are plenty of ways to figure it out. So now that means we're going to get this anion, and it's going to donate its proton to water to make H3O plus. If you are a lazy chemist, let's pick a different color. I'm going to write it in the top here. And you choose not to write the water, which is fine. Then you would get this. And again, this, and this, they are exactly the same. Okay, so it doesn't matter. They're used interchangeably. So what's going to happen here when we do our ice table, because water is a liquid, it's going to cross out and everything else is aqueous, which can be included in the equilibrium law. No solids and liquids. So we have 0.1 molar of the acid. And what happens is, so you can think of it like in your head, you have the acid concentration. It's put into solution. We have 0 ions to start with, and then it's going to dissociate, which means, so if these are 0, then it has to be positive in this direction, much like you're used to, and this one goes down. Okay, and there's 2 choices. You're either given the equilibrium constant or you're given something at equilibrium. So here, because the question says calculate Ka, that's what we're asked, then we must be told something at equilibrium. So similar to the acid-base questions, sometimes it doesn't come out and say at equilibrium, not acid-base, solubility, at equilibrium, blah, 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 but it gives you, you're also given this pH here, okay? So lots of exclamation points. pH is used to calculate equilibrium concentrations. So make some stars. Those are terrible stars. Make a box, use a different color, okay? So what that means is then you've got, whether you use H plus or H3O plus, it's the same. Okay, so this value goes in here. Okay, and that also then, because that's X, that goes over here as well. Okay, and can be used over here to calculate this value as well. Okay, you guys have 2 spots there. I'm going to try to squish it into here so that it's all on the same screen, but you can keep going in that whole spot there. Okay, so now we have, I'm going to switch back maybe to orange. Now we can do Ka, which is products over reactants. We cross the water out because it is a liquid, no solids and liquids. .8 times 10 to the negative 4, which is pretty small. So that's probably a great value. Great value, yes, to have for a weak acid. And then there's another thing here it says to do, which is pKa. So pKa is going to be important when we talk about titrations and buffers. Anytime you see P in front of something, that means the power of it. So pH is negative log, POH negative log. OH So pKa is negative log Ka. So negative log okay. So if you're keeping a formula sheet, you can write that on there. Maybe even this you want to put on there if you didn't already. I think that's it maybe. Products over reactants, those things might help you. Okay, so there is a blank. So now on to the next example. A 1 molar solution of acetic acid has a Ka value of 1.8 times 10 to negative 5. So again, maybe you're used to this acid by now, or that's weak. You're given a Ka value, which is not very large. That can tell you it's weak, which means we have to do ice. Again, an acid's a donor to the water. 1 molar, cross out the water, 0, 0, minus x, 1 minus x, plus x, x. Okay, but this time we are asked to find the equilibrium concentrations and we're asked to find the pH, but we're given the Ka. So that means we are going to use our equilibrium expression to solve for x, and then we're going to find pH. And we have 2 of the same, which makes x squared in the top, which means that in order to solve here, we would have to use the quadratic formula. Now, that's fine, you can do that, or we can use the 100 rule, okay? And we're going to use the 100 rule here. So we have a Ka value, which is 1.8 times 10 to the negative 5, which is much, much smaller than 1. So again, is it 2 decimal places smaller? Yes. This is that you can rewrite 1 as 1 times 10 to the power of 1, which is at least, this is 4 decimal places difference, even 5 decimal places difference. All we need, 100, is 2 decimal places. And like I said, your textbook in this section uses the 100 rule when it shouldn't. So since Ka is much, much less than 1, then we're going to do, say, 1 minus x is approximately equal to 1. So then in the bottom of our fraction here, we're going to have 1. So then we don't have to use the quadratic formula to solve for this. We can just square root. Okay, I'm going to try to fit all this on this slide. So I'm going to cross multiply. So even though it's 1 down here, I'll show the work. And then to get rid of the squared, I'm just going to square root. And we actually don't need the negative one, the negative answer to the root, because then we want to have a positive x value. So the square root is the x value here and the x value there, which means that when we find the pH, which I'm going to do on the other side here. Let me cut, get rid of this. So now the concentration at equilibrium. Oops, I did too many. Five, 7, 6. So close to 1, right? So you could just write 1, that's fine. And then the H3O plus and the acetate anion are equal, which is the X value and then the pH. Should be acidic, but not too acidic. .37. Okay, so you can check the logic of your answers here, that it's acidic, but not too acidic. Okay, so amines are weak bases. So again, they kind of look like ammonia, which is NH3. How else could you tell this is a base? We're asked to calculate pKb. B stands for base. And so that's going to, and again, actually there are very few weak bases that are pertinent. Usually it'll be ammonia, which you're used, again, if you do a couple of these questions, you'll be used to it. So when you do these problems, you'll just kind of get used to these. And actually, I'm going to add in here, let's find the pH too, which is a common question you'll be asked. Okay, so this time when we write the equilibrium expression, it is a little bit easier if you leave the water in, because what's going to happen is this is a proton donor. Let's pick a blue color. Proton acceptor, not donor, sorry. So that means that instead of NH2, it's going to be NH3. It has accepted a proton. It also is going to have a positive charge. But actually the cation, even the NH3, that's not really important. What is important is if it accepts a proton, then that comes from the water, which means that water has given away one of its protons to make OH. So now when you have a weak base, even though there is no hydroxide in the formula, where does the hydroxide come from? Oh, it comes from the water. Point 1. And again, 0, 0, plus x, plus x. We're only going to do one at a time. You're never going to have to worry about 2x or anything like that. And now we're not given the Kb, we are asked to calculate it. So we are given this other piece of information here, percent ionization. So similar to pH, percent ionization tells us what the concentration is at equilibrium. And that makes sense. What's the concentration of ions that are formed? So I'm going to keep with this orange color here. So percent ionization is, pick one of the ions, it doesn't matter, over the base. And it doesn't matter because they're 1-to-1, right? So they're both the same. So 6.3, and whether you use X or if you leave it as hydroxide, it doesn't matter. Whoa, oops, sorry. 0.1. Okay, so now there are a bunch of ways to solve for this. So some of your brains will automatically change the percentage into a usable number by dividing by 100. Or to get rid of the 100 on this side, then you divide by 100 on this side. Either way. So X is 0.0063 times 0.1, which is going to give us, sorry, I put too many decimals in here. There we go, 2 decimal places. And then put times 0.1 is 0.0063 in the end here. Skip too many steps. So now this number tells us our X value, which goes over here. This is minus X. Which does give us a tiny number. And like I said, your textbook will use the 0.1. They won't subtract the X anyways. So it really actually doesn't matter which you choose. Okay. So products over reactants. These are terrible square brackets, sorry. .24 times 10 to the negative 4. So that is a small number. That makes sense based on that. If it's a small number, then that is going to be a weak base. Okay, so we were asked to calculate Kb. It's only 6.3% ionization. There's lots of ways to tell. Okay, so now when we do pKb, again, you're going to do, I'm going to insert a new slide here if I can, so I have a little bit more space. So now when you do pKb, similar to pKa, that's always going to be negative log. 4.24 times 10 to the negative 4, which is 3.37. You're also asked to calculate Kb, so then you need this formula here, Ka Kb equals Kw. So our Kb value is small, but this is a base. So even though we can use the property of autoionization of water, this Kw value here, which is reference, Ka should be even tinier, okay? Because we definitely are dealing with a weak base here. So we're going to divide it, and you really have to be careful about how you divide scientific notation numbers in your calculator. So 2.36 times 10 to the negative 11. And then when you are going to find the pH of a base, there are two options. So we found, so you can use this expression and the number you just found here, used here. Most people will actually just do POH. So we found the OH concentration here. So they will use that. I'm running out of room, so I'm just going to keep going on the same line, sorry. And then they will use this expression. So again, if you are a formula kind of person, this one is a common one too. So pH is going to be 14 minus POH. So 14 minus 2.2 is 11.8, which makes much more sense for a base. But again, not too basic, not super close to 14, just a little bit above 7. Okay, so try these questions. I know that they are easy. Give yourself a chance to be